Oh, that's some great music. Hello, everyone. I am Reginald Braithwaite, and I think my head is recovered enough to proceed. So let's talk about duck typing, compatibility, and the adapter pattern. I tweeted earlier, I warned everyone that there would be this and prototypes in this talk, so if that offends you greatly, either start composing your objections now or excuse yourself until later. Now, this is a shortish talk, as these things go, so I'm going to jump right into it. And we'll get started with something that I think everyone is very familiar with, duck typing. Now, there are some complicated and long-winded things you can say about it that makes it seem like there's some sort of computer science rigorous basis for it. But we know better. It's really simple. These things taste like fruit. They also look like fruit and smell like fruit. These things taste like fruit, look like fruit, and if you're sufficiently generous, smell like fruit. The whole basis of programming with duck typing is to write code that is really based on and depends upon things tasting like fruit rather than things actually being fruit. We don't get hung up on whether something is fruit. As long as it tastes, smells, and looks like fruit, that's good enough for dinner. Duck typing is really a compatibility technique. It's a way of getting multiple things, and we can use a long and complicated word like polymorphism. But really, it's all about compatibility and making it easy to make things compatible, which, while you do give certain things up that other people at other conferences, say for Java, will tell you is useful, and there are some trade-offs, it does also make it easy to make software that's made out of separate parts that are compatible and can be exchanged, much as having an S100 bus or other bus standard makes it easy for people to make cards that fit into a PC of a certain kind. It's not complicated. Now, let's look at a problem that is often solved with duck typing. Don't worry about the writing on the slides. Those are for people who look at the slides later, or to remind me what I'm supposed to say. Now, here's one of my favorite problems. Anybody know what this is? Not bad. Yes, you're right. It is implemented in the game of life, and it happens to be a universal Turing machine, or rather a section of a universal Turing machine implemented in the game of life. I consider this awesome, and if I understood it, that's what my talk would be about. But let's talk about a really naive implementation of Conway's game of life. There's a whole bunch of things that we would do, possibly involving reactive functional programming or so on, but we're going to keep this simple and somewhat traditional. We know that Conway's game of life is a two-state cellular automata, meaning that there are individual cells that all make independent decisions about what state they're in. Two-state, there are two states, normally called alive and dead. And when we say that they make independent decisions, they make a decision based on information available to them in their neighborhood. There's no action at a distance in a cellular automata. And Conway's game of life is like that. The rules are very simple. If a cell is alive and it has 2 or 3 alive neighbors, it will be alive in the next generation. If a cell is not alive and it has exactly 3 neighbors, it will be alive in the next generation. Any other configuration in the cell will not be alive in the next generation. I believe this is written as 2.3/3 life or 3/2.3 life, and there are other variations that we can have. But this is the one that we're going to work with today. If there's anyone who's incredibly confused about all that, I apologize, but there isn't time for me to write another presentation right now. So let's talk about an implementation. As we can expect, being complete object-oriented people and not having, embraced JavaScript, Elongé, and all of its talk of functions, we need cells. We need some concept of a universe or something else. I call it a universe, but you could call it neighborhoods, something that manages having more than one cell. And while there are other pieces, one of the pieces we'll talk about today is some kind of a view, some kind of a thing for presenting what our universe is doing. And those three things together are what we're going to talk about today. Now, in actual fact, we rarely write stuff this simple, and if we do it in one particular sitting, and we don't need to do a lot of talking about design patterns and so on. But when looking at something extremely simple, if we hand wave over the fact that there are other ways to do it, it does allow us to really focus on a particular technique. So let's look at a cell. One of the things a cell needs to do is know what its neighbors are, because part of the rules are that its next state is based on the states of its neighbors. If there's a rule that its next state is based on its states of its neighbors, a cell needs to know something about its own state. So here's some code. Oh dear, this. And worse, I'm pretty sure that in order to make that thing do anything useful, we need to use new. I warned you about prototype and this, and now I'm throwing new in, and I didn't even give you a disclaimer about that. My deepest apologies, but there's no time for me to rewrite this. Let that be an exercise for you at home. We're going to compound my errors and actually write a setter and a getter. I can't believe I've written entire books saying you should avoid setters and getters, and that's not really object-oriented, but for the purpose of this argument, we think it's a good idea to have a neighbors getter and a neighbors setter. We have the same thing for alive. Essentially, this is not an object in the truest small-talk sense of the word. And if it's not clear why that's the case, spend some time with some of Crockford's books and look at Smalltalk 80, as he mentioned earlier. Now, those things alone are not enough. We have to have some way of managing moving through time. We have our cell with its neighbors and state, and we're going to need something that handles transformation of state. There are other ways to do this, but we're going to say that a cell is responsible for its own next state. That's the way it's described by John Conway, and he should know. He's the authority. And we're going to say that a universe, as we sort of mentioned earlier, has some understanding of neighborhoods and of transformation of states. And here we go with the cells. Its next state will be alive, and there's the logic that we described earlier. And we have some idea of a universe iterating. It does it in two steps. At first, it looks at all the states and says, what will your next state be? And then it applies the next state to all of the cells. If you try to interleave those and don't do it in two separate states, bad things happen. I leave it as an exercise for those who have never implemented life to understand why you first have to query and then write. At some point, we want to display it. Perhaps we will use something like this, but perhaps not. For the sake of this, since we're talking about JavaScript, we'll do something with a canvas. Our view will be responsible for drawing a cell. And here's some code for that. And it's probably a terrible way to do this with a canvas, but the thing that's most interesting here is that it has a bit of a helper function, cell color, which you'll see in a moment really shouldn't have this associated with it. I don't know who wrote this code. Because there's actually no state of the view involved in this, so that's a really bad idea. But moving right along, it's very simple. If the cell's alive, it will be drawn in white, and if the cell's dead, or not alive, I should say, it will be black. All right. Like all software, it's not long before we have changes in requirements. Anyone here not get this? We decide we want to display life in color. A common scheme is that not alive is black, but the color of an alive cell reflects how long it has been alive. So we're going to design a color cell, and where before it used to have an alive, now it has an age. Neighbors are the same as our previous setter and getter. Our age setter and getter looks pretty simple. But when it comes time to move through time, things are a little different. The basic structure of the function is the same, and some of you will immediately say, we should refactor this so that the sameness can be extracted. Okay. But the key here is that when we say something is alive, we increment its age, whereas previously we just say it's alive. And when we see something is no longer alive, we set its age to 0. Otherwise, it's very, very similar. And when we iterate in our universe over all the cells, instead of asking each cell for its next alive, and then setting its next alive, or setting its alive to whatever the next alive was, we're now getting its age and setting its age. You know, I do stuff like this all the time. Change the name of a function, when we upgrade, blah, 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 hardly any changes, a bit of logic. It's done, ship it, customers are happy, and nobody wants to hear about refactoring this. But for the purpose of argument, let's take a look at coloring cells. Drawing now is different. Instead of black and white, we've got a bunch of colors, and we set it according to the age, and there's a little bit of extra logic that checks that if the age is greater than a certain amount, it's still going to be red. Very simple rewrite. But something doesn't fit. The methods for our original standard cell, neighbors, set neighbors, alive, next alive. But for color cell, we've got age, set age, and next age. As we discussed earlier, that's because we're no longer tracking aliveness, we're tracking age. And when we make this change, we changed standard cell into color cell. We changed the way the view worked, which makes sense, because the view is the thing we actually wanted to change. But we also changed the way the universe worked. The universe, really, the logic of that is kind of, it's almost irrelevant, but we had to change it because the name of the function changed, or rather, the name of the method changed. The interface changed. And our problem is this coupling of universe to cells interface. How are we doing on time? Not too bad. So let's look at how smart people solve this problem. It's that simple. If colored cells and standard cells both behaved the same way, had the same interface, we wouldn't have to change the way universe works. So we can give a color cell an alive method. We can give it a set alive method. And we do some monkeying. If you say it's alive, add 1 to its age. If you say it's not alive, make it 0. If you ask it whether it's alive, check whether its age is greater than 0. Now our next alive doesn't need to be any different than it was before. Our universe works. And if we ask a color cell, what are your methods? We get all the original color cell methods that we need for drawing it, plus the original standard cell methods that we need so that the universe does not have to be rewritten. Ta-da! Tastes like a standard cell, just like it says. We've decoupled our universe from our changes to cell. But nothing is free. We've added complexity to cell. And this is because of this rule. Anytime you make something more flexible, you make one thing easier, but you make the other thing more complicated to support that. Oh. And what I'm here to talk about today is another way. Instead of making colored cells behave like standard cells, let's make another thing that behaves like a standard cell, but is implemented in terms of a colored cell. If you're really into old-fashioned books about object-oriented design and so on, this is often called the was-a relationship. So we have a new kind of object, an as standard, which wraps around a colored cell. And anytime you want something that tastes like a standard cell, you pass it a colored cell and get back an as standard. Implementing it is pretty straightforward. Hopefully you have some libraries that can forward functions, but if you don't, here it is written out. The neighbors and set neighbors methods are both being forwarded to the wrapped color cell. You ask it to be alive, and it in turn queries the colored cell and asks it whether its age is greater than 0. If you set alive, it's the same thing we did before, but all of this is happening in our as standard wrapper rather than in the colored cell. Same with its next alive. And as a result, our as standard has the exact same methods as the original standard cell, but it's implemented by wrapping around a colored cell. So now, if we upgrade our, that should be colored cell, spelling mistake. Now, if we upgrade our application, view can depend upon colored cell, which is what we want, because the view is showing colors. But the universe can depend upon as standard instead of depending upon colored cell. So the universe does not have to change as long as we give it an as standard instead of giving it a colored cell. This is good. This is very good. We have made sure that colored cell is responsible for managing cells that have color. And this business of backward compatibility that we want to do to avoid having to couple our changes to other modules, other classes, and so on, is isolated in the as standard object. It's true we still have the same amount of additional complexity. That can't go away. But we've isolated it in one place rather than smearing it over the application or stuffing colored cell with additional responsibilities. Our as standard is known as an adapter. And there's some complicated stuff you can get off Wikipedia. You don't have to ask me about it. And furthermore, what I just showed you, making a wrapping adapter, is not the only way to do it. We can take something from C++ and create something called a copy constructor. That's another way to create an adapter. You make a colored if you handed it a standard, or you make a standard by handing it a colored. That also works. And there's more. With ES6, one of the things that I didn't hear come up, we can have proxies. We can monitor changes to an object. One of the things we can do with that is create something called co-proxies. We could create a colored cell and a standard cell that each update each other when one is changed. This is very important if you're dealing with an application where two things need to own an object at the same time and they each want to talk to a different interface. That's another option instead of using a wrapper. Not too bad. Now we're getting close to the end of my talk about adapters. This pattern I showed you for a very small, incredibly simple example. But the general principles are much larger than just a hacked together possible implementation of the game of life that uses all of the bad parts of JavaScript, namely new, this, and prototypes. Adapters allow us to separate two important concerns: what a model does and how you interact with it. Adapters do more. Because of this separation, they allow us to focus changes in one place rather than smearing them all over an application. And as a result of that, if we scale up from looking at a couple of models or a couple of classes to software in the large, software at scale, adapters can help us decouple entire modules. It's not just a technique for classes, it's a technique for modules, packages, anything larger, anything that has an interface and a little wall around it and things interact with it. Adapters allow us to have more than one interface for an implementation, be it a class, a function, or a module. If you read about adapters and do a quick search, the usual example case is solving a compatibility problem. You're given this library, but you want to talk to it in a different way, or there's another library that does the same thing but has a different interface, so you write an adapter so it works like the library you already have. It's always sort of given as an after-the-fact technique. However, we can also use them to do forward-going programming in a more safe manner. Because if you have adapters and you can focus your changes in one place, that allows us to make changes more safely, with fewer issues. We don't have time today to go into it, but if you think about the way testing works, adapters allow us to test a lot of logic without having to rewrite all of our tests as well as rewriting our application code. And that's a very important thing for the safety of an application, because the more you change your test, the more risk there is that the test will test the wrong thing. Fundamentally, adapters are an important tool for anyone who's building software at scale. Whether that scale be the number of lines of code, the amount of time the software is expected to live in production, or the size of the team that are interacting with it. And that's what I have to say about adapters. Now I see we have some time. One more thing. I mentioned packages earlier. The thing about packages is that when you're holding a version-shaped hammer, everything looks like a just migrate the software to the latest version-shaped nail. But that's a problem because, as we know from bitter experience, packages have interlocking, dependencies. So when you upgrade one, you have to upgrade another. You're making changes all through your application. You're retesting everything, rewriting tests. It's a nightmare. You order a package, you never have any idea how much work is going to be delivered to your door. So as a result, we use semantic versioning as a way of saying, whoa, we just bumped a major version. Look out. You're going to have to rewrite everything. And the problem is, semantic versioning really, really values backward compatibility. As much as possible, when you're writing packages in a semantic version package manager, you really, really try to maintain backward compatibility at all costs, which takes us down the road of when we made a colored cell that still behaved like a standard cell for backward compatibility, but at the level of packages. And this holds us back by adding this complexity, by adding work to what we're doing. It makes it harder for us to make new models, new ways of doing things. But of course, if you break backward compatibility, you create bugs for your clientele who cannot upgrade to the latest version, because bug fixes and new functionality sort of have to go together the way software is modeled. One use for adapters is to decouple issues of compatibility from issues of progress. If you could rewrite your module such that it breaks all backward compatibility but add an adapter, prestolicious, you can have a whole new model and have a way for older clients to interact with it without it being cluttered with the backward compatibility issues. That would give us a great deal of safety. People need not rewrite their entire application, and they could get the benefit of things like bug fixes or performance enhancements from tail call optimizations or whatever else might be super exciting about the latest version of a package that we want to release. So this leads me to ask, if a package manager was sort of adapter aware, what would it look like? Well, for one thing, interfaces and implementations would be separately versioned. Right now, there's just one thing, 3.4.123. And that represents, the 3 represents a change of interface, I think, and the 4 and the 123 represent some changes of implementation, but anything with a 3 should be backward compatible with anything without a 3, unless it's CoffeeScript. But that's the general idea. But they're all locked together. Whereas, if they were independent, you might have version 3.1 of the interface and version 57 of the implementation, and you might say, there's a many-to-many relationship between these two things, because version 57 of the implementation has adapters for version 2 of the interface, but not version 1. So we know that version 57 can work with clients that are expecting version 2.x of the interface or version 3 of the interface. Perhaps version 55 of the implementation only talks to version 2 of the interface. And that way, clients could specify what interface they require and what implementations they would like to have, separately and independently of each other. And this would allow old clients to get bug fixes without extensive rewrites. As you continue to iterate and add new functionality, your adapters to the old ones give you that backward compatibility. And of course, when they do want to upgrade, they can take advantage of the new functionality as well. My feeling is that whether it's this specific technique or this general idea, pursuing the idea of decoupling interfaces from implementations has the potential to radically change the way we develop software at scale. And by scale, again, I say size, time, or team. And that leaves me really kind of going, And not just in terms of, oh, cool, adapter pattern, but if we take a step back, you know, programmers love to generalize everything. If we take a step back, we see that the technique here, the way we arrived at this, was by taking a small pattern that is described as being used for one thing, fixing a compatibility problem, and then saying, you know, what if it was a golden hammer? What if every problem looked like an adapter nail to fix? What if we went beyond just fixing problems, but said, let's use this as a design technique? What if we turned it up to 11? What would package managers look like? What would a programming language look like if adapters were somehow baked into the actual syntax and compilation of the language? What would a package manager look like? What would tests look like? Would there be some magic way that tests would specify what versions they need or test and so on, and it would all integrate and run automatically, and you could check on it? What would it look like if Git was integrated with adapters? So that you would just say, hey, I want this package, and it would check out the correct version or something for you. All these things arise when you take one thing and kind of, instead of just using it, kind of think about it for a while and say, what if? And I find that a lot of the time you say, what if? But sometimes you say, And when you do get that motion, that provides a lot of food for thought. And with that, I will say, try. Tack så mycket.